one last little concept. The concept of energy is applied to the Universal Law of Gravitation. When the force of gravity is simply mg, where g is 9.8, the potential energy, we integrated the force over the distance and came up with the potential energy equation of mgy. That works just fine as long as g is constant for your whole problem. So anywhere on the Earth, near the Earth, this works perfectly fine. But if we get to distances far from the Earth, say we're shooting a rocket into the air. If we launch a rocket, now this isn't a personal hobby rocket, so big time old rocket. If it gets launched, say at 10 kilometers per second, moving really, really fast, it's going to go really, really far. It's going to go beyond the boundaries where g is 9.8. So that won't work anymore. The mgy will not work in terms of energy. Energy can still be used I'm going to make another not so good assumption. We're going to ignore air resistance at the moment.
It's not so slow, you know.
Exactly. Now we know when we deal with distances far from the Earth on an astronomical scale, the force of gravity, the actual equation we needed to use was the big G, the universal law of gravitation, it's 6.67 times 10 to the negative 11, times the two masses involved in the attraction over r squared, where r was the distance from center to center. Turns out, when we integrate this force with respect to distance, integral of 1 over r squared is what? 1 over r squared is the same thing as r to the negative 2. So r to the negative 1 over negative 1. The result, we get a different potential energy equation. But we get it the same way, we integrate it. 1 over r squared integral negative 1 over r. So the equation for potential energy, when we're dealing with far distances from the Earth, is negative g m1 m2 over r. It's not r squared anymore. We integrated. So it's now just over r. The negative sign is part of the equation. That means we're going to get negative values for our potential energy regardless of where we're at, just because there's a negative sign in the function, in the equation itself. So, gravitational potential energy has a different form if we deal far distances from the Earth. Please keep in mind, when you solve any problem at all, you can use one or the other. You cannot intermix those two potential energy equations in one given problem. You can use either mgy or you use the negative gmm over r. You choose. Now, to choose, if your problem is on the Earth, if your object's going to stay near the Earth, you just use mgy. That's perfectly fine. If your problem you think is going to go far from the Earth, for example, launching something that fast, I would expect it to go pretty high, then we would use this equation for the whole problem. Okay. This equation, still perfectly valid, which, remember, is the same thing as this equation, whichever form you like to use it in. It has not changed our overall conservation of energy equation. The only thing that is changing is the potential energy equation itself. Please, also one other little note. If we're using this equation for our potential energy, You cannot say potential energy is 0 wherever you want it to be. The only place this is 0, what type of R value do you have to get U to be 0?
Infinity.
If R is 0, you get infinite.
Make it infinite.
So R needs to be very, very large, infinitely large, to get 0. So the only place the potential energy now is 0 is infinitely far away. So, for example, if we launch a rocket with a speed of 10 kilometers per second, how high is it going to go? Well, we have to have potential energy initially. R is still the distance from center to center, so it's the distance from the center of the Earth to the center of the rocket, which is going to be the radius of the Earth. Kinetic energy, so let's put these in. Instead of M1 and M2, what are the two objects involved? Earth and the rocket. The kinetic energy of the rocket, so 1/2 mass of the rocket times its initial speed squared. We know its initial speed. We're ignoring air resistance, so we don't need to worry about this work term. If we wanted to include air resistance, we would need to know an average value of the force as it was applied through the atmosphere. So the initial potential energy plus the initial kinetic energy, finally there's still going to be potential energy as well. We're going to be at a new final location. Kinetic energy, finally, what will that be? 0. When it reaches its maximum height, at that instant, it will not be moving. The gravity is going to pull it back down and it will come back towards the Earth. So the main difference is that you will have potential energy initially and finally, your equation. Turns out there's a mass of the rocket in every term. We know big G, that's a constant. We know the mass of the Earth, or at least we can look it up. It's in our book and on the test notes. We know the radius of the Earth. We were told how fast it was going. So our finals are only a known. To get our final, though, we need to cross multiply. So our final comes up to this side. All this stuff comes down to the other side. So G is 6.67 times 10 to the negative 11. Mass of the Earth, 5.98 times 10 to the 24, I believe. If someone wouldn't mind looking up the radius, it's like 6.3 something. I think it's in the back cover of your book.
6.37 times 10 to the 6th.
Thank you. So G, mass of the Earth, radius of the Earth. Initial speed needs to be in meters per second, so 10,000 meters per second. Plug and chug all of that in. This is when I wish my calculator would work. those of you plugging it into, let me know. I get 3.16 times 10 to the 7th meters. Where will this be measured from, by the way? Center of the Earth out to where the rocket is now. So does that quite answer the question? No. To answer how high will it go, we need to subtract from this the radius of the Earth. So the height that would be how high it goes, assuming I plug those numbers in correctly.